Welcome to this presentation on area based approximation. We will discuss trapezoidal forward and backward approximations. We will discuss the pros and cons of each of these. We will present some examples. We will show some Scilab code and the resulting output. Let us consider the problem of finding the area under this curve. This is equivalent to integration. So if the area under the curve u is given by y, then it is given by the blue shaded area plus the red shaded area, and the blue shaded area is given by y of k minus 1, the area obtained at the time instant k minus 1, plus the red shaded area. Here we will use trapezoidal rule. Here is the height uk, here is the height u of k minus 1, Ts is the gap between the two. So we have applied trapezoidal rule to get this. Of course, if it is a straight line, this is what we get, but the actual curve could be a continuous curve which need not be straight between these 2 points. As a result, we call it an approximation. This is trapezoidal approximation, because the area under this curve in one sampling instant is done with trapezoidal approximation. This is the formula we derived in the previous slide. Let us take the Z transform, use the shifting rule. Z transform of y of k is y of z. Here it is z inverse into y of z. So Ts by 2 times u of z, plus here we will get z inverse into u of z. Bring this y to this side, equals the remaining things. Now let us common factor this out, 1 minus z inverse, here also it is 1 minus z inverse times Ts by 2, and of course we have to put this u of z. In the next slide, let us start with this. Let us take this 1 minus z inverse to the denominator here, multiplied by this u of z. Multiply both numerator and denominator by z, we get z plus 1 by z minus 1 times u of z. So the integrator has a transfer function. Remember, we started with 1 over s. Why 1 over s? Because we found the area under the curve. So the integrator has a transfer function g I of z given by only this part, which is Ts by 2 times z plus 1 by z minus 1. We can denote the poles and zeros here. Here is the pole at z equals 1, 0 at z equals minus 1, and recall that this is a low pass filter, which is in agreement with the pole 0 location based filtering theory that we presented earlier, and of course it is also consistent with the integration operation, which is a low pass filtering operation. It is a smoothing operation. So we write it as 1 over s as the discrete equivalent of the value given here, which is Ts by 2 times z plus 1 by z minus 1, same as what we have here. This is also known as the Tustin or bilinear approximation. So let us now calculate the Tustin bilinear approximation of 1 over s plus 1 with Ts equals 0.1, sampling period Ts equals 0.1. So recall the substitution strategy. Wherever 1 over s is there, we have to put this entire thing. This is what we obtained in the previous slide. So I am going to write this as gd of z when I substitute in the place of s this expression. In the place of s, I have done this. Notice that what I have here is 1 over s. So in the place of s, I have to put the reciprocal of this. So the reciprocal of the first term is 2 over Ts, and for the second term we get z minus 1 by z plus 1 plus 1. Let us simplify this. Ts into z plus 1 will come here and also in the numerator. and then let us group the terms. So here the coefficient of z is 2, here the coefficient of z is Ts, so I get this, and the constant term is -2 here and then Ts here. Let us see how we get this expression from here. Bring this Ts to the denominator, this will be 2.1 by 0.1, so it is 21, this will be minus 1.9 by 0.1 and hence minus 19. That is how we get this. Here is the Scilab code for this from a file horner-test.sce. I open a diary so that the result of all these calculations go into this diary. I define s and z to be polynomials. I define this transfer function 1 over c plus 1 as a continuous transfer function. Then Ts, the sampling time is 0.1, and I invoke the inbuilt Scilab function called Horner. The transfer function GA is given here. Here is the approximation rule. When I do this, I get the result. Here is the output of the diary file. The transfer function is 1 over s in the continuous time domain. The sampling time is 0.1, and the result of this GD is given here. This is exactly what we obtained in the previous slide. I would suggest that you try out this example using Scilab and also a few more examples. Now let us derive the derivative mode approximation from this. This is the trapezoidal approximation we obtained earlier. For derivative mode, I have to use the reciprocal of this. So I get S having the reciprocal of this term on the right hand side. Of course, this is a high pass filter because it has a 0 at z equals 1 and a pole at -1. Hence, it produces in partial fraction expansion a term of this form z over z plus 1. So when I invert this, I will get z over z plus 1. Important thing to remember is the denominator. You will have z plus 1. What happens when I invert it? I get -1 to the power n. And what happens to this? This is highly oscillatory. This results in wildly oscillating control effort. Why control effort? We assume that we have a derivative mode given by s. Now supposing I were to use this in the place of this s, I will get z over z plus 1. When I invert it, I will get -1 to the power n. So our discrete time implementation will oscillate. We will see the importance of this while designing controllers, especially in pole placement controllers. Because the method we tried earlier gave a problem for derivative mode, we will consider another method, backward difference method. We go back to our method to calculate the area. We replace the area that we obtained using trapezoidal approximation with a rectangular approximation. So let us bring this y of k minus 1 to the left hand side. I get this. Similarly, z transform of u, bring it to the right hand side. Simplifying, we get Ts into z over z minus 1 into u of z. So 1 over s has this whole thing. Here is the Laplace domain transfer function 1 over s for integration. This is the backward difference approximation for integration. So the reciprocal of this is 1 over Ts into z minus 1 by z. And notice that z plus 1 that we had in the denominator earlier has been replaced with z now. It is high pass because it still has a 0 at z equals 1, but it no longer has a pole at z equals -1. It has the same gain as before and there are no oscillations as I mentioned earlier. So let us take up an example. Let us discretize 1 over s plus 1 with Ts equals 0.1 but with backward difference approximation approach. So here is the substitution formula. So Gd of z is, in the place of s we have to put this whole thing, the reciprocal of this as before, because this is the equivalent of 1 over s. So for s I need to take the reciprocal. Let us simplify this, group the terms. So 1 plus Ts into z minus 1 and let us substitute the values. So here it is 1.1 divided by 0.1, so which will be 11 here and minus 10 here. So 11z and minus 10. Here is the Scilab code for that from the file Horner back test.ace. The explanation is similar to what we did before, so I will skip this and here is the result. Once again we get the same answer, z over 11z minus 10. I would encourage you to try this out again. We will also consider forward difference. Previously we had used Ts into uk, now you use Ts of uk minus 1. So let us simplify this, Ts into z minus 1 into u of z, Ts into z minus 1 into u of z. When I simplify this I get this expression and then multiply both numerator and denominator by z, you get this expression times u of z and hence we get the formula 1 over s gives rise to Ts by z minus 1 and hence s is z minus 1 by Ts. This is also high pass because it has a 0 at z equals 1, it also has no oscillations, it has the same gain. In this particular case the value is the same as the step response equivalent. I would want you to go back to the previous recording and check this, but that is true only in this particular case. In general these two results are different, that is step response equivalent is not the same as forward difference method, it happens to be that way for this particular example. So let us summarize the area based approximations. We have trapezoidal approximation given by this. For integral this is the best approximation. For derivative we got oscillatory response, so we did not like this. Then we considered backward difference 1 over s given by this expression. This works fine, we have no problem as far as integral is concerned. Derivative it works fine, we will have z minus 1 by z as the reciprocal. What about forward difference? It turns out there is a problem for not for integral mode but for derivative mode. So integral mode it works fine, but derivative mode when I take a reciprocal of this, what happens? Notice that we will have z minus 1 by Ts. So z minus 1 by Ts is not causal and hence it cannot be implemented, not causal. So we conclude that only the backward difference is suitable for derivative because here we got oscillatory response, here we got unimplementable form. This is the only thing that works for derivative mode, which is the backward difference method amongst the three methods we considered here. Any one of these can be used for integral and hence there are many possibilities for discretization. So next question is, should we use step response method or area based approximation method? So you will agree that area based approximation is easier to calculate, but it does not work in case of time delays. except when delay is an integral multiple of sampling period, whereas the step response or zero order hold approach can handle delays as well. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.